Good evening, dear students. Today we'll be discussing a next session of circles, whatever we have discussed in the last class, and this is on common tangents to two circles. Okay. Before I proceed further, could you please confirm that you are able to hear my voice very clearly and able to view the screen properly, dear students?
Yes, sir.
Okay, great. Thank you. Thanks for the confirmation. Okay, now to understand, the common tangents to two circles. So let us first, draw the diagram, and then let me explain you. Okay, so when we have two circles, so if I give a symbolic representation of the circle, something like this. This is one circle, and let me draw another circle here. Yeah. Let us consider these two circles. Now, the common tangents means is that a straight line which is tangent to both the circles. That is what is called common tangents to two circles. Now, what type of common tangents possible? Okay. The first type of common tangents possible, dear students, is that I'm going to draw in blue color, is that is called the direct common tangent. Okay, so what is direct common tangent? If I draw this thing and it is in blue color, so it is a kind of a straight line which something like this, and here also you can draw. If I draw it properly, if you look into this, two straight lines, what I draw in the blue color, these are called the direct common tangents. Why they are known as direct common tangent? Because direct common tangent is a tangent touching two circles at different points and not intersecting the line of centers between the centers. Okay, so not intersecting the lines of centers between the centers. What does it mean? It means is that both these circles have their center, right? So for example, this circle is having a center at this point, and this circle is having a center at this point. Now we can draw a line joining their centers. Correct? So as these blue lines, what you see, dear students, they are not intersecting the line of centers between the centers, then it is known as the direct common tangent. So what we say is that, if I write in a different color, this is known as direct common tangent. This is direct common tangent. Let me first explain you. After that, I will give you a formal definition. This is also direct common tangent. Okay. Now the next point what comes, dear students, is called the transverse common tangent. What is that? Transverse common tangent is a tangent touching two circles at different points okay, and intersecting the line of centers between the centers. Okay, so if I draw the transverse common tangent by means of green line, so it will be something like this. Just a minute. If you see, this is one tangent, though it doesn't looks like a tangent, it looks like it is intersecting, but just you can consider the precision of my drawing. And this is also not exactly touching, so just give me a minute. Yeah, that green line and another green one. Yes, in fact the second one is very perfect. So what you see, dear students, the two green lines, okay, whatever I have done, the two green lines, what I have drawn here, if you see, is that they intersect, okay, and they intersect, touching, the line of centers between the centers, which is there in the red line. Correct, dear students? So this is known as the transverse common tangent. So this is known as the, if I write it down, this is known as the transverse common tangent. So this is, in fact, I can include both. This is known as transverse common tangent. Correct, dear students? Now, the next one what comes is that, so there are two types we have learned so far, and the third one is known as the common tangent. So common tangent at a point of contact is a tangent touching two circles at the same point. Now, dear students, if I just give you a visual representation of the statement, I just say, it is possible that when the circles touches each other, externally or internally, then only we can get the, the common, tangent. So let me show you how the common tangent is actually getting formed. Okay. So, if I draw a circle, let me draw the circle first. Suppose this is one circle, and another circle I am drawing in a different color, suppose in this color, but they need to touch each other externally. So if you see, they touches each other externally. So now, if I draw a straight line, means which is a tangent, and if I draw this in blue color, so if you see this straight line, this is actually a common tangent. Okay, and also I can give you that another illustration where the common tangent is coming, like that when the two circles are touches each other, internally. So how it looks like this. You see, these two circles touches each other internally. So now what I'm going to do is that I'm going to draw a tangent that is also in the blue color. Sorry. If you see, these two blue lines are actually, that is known as common tangent. So this one and this one, this we can say it is a common tangent. So dear students, our idea about the direct common tangent, transverse common tangent and common tangent is clear. Now as it is clear, so let me give you the definition now. As I said that the formal definition I'll give. There are three types of common tangents, and here it is. Okay, dear students, so the direct common tangent, a tangent touching two circles at different points and not intersecting the line of centers between the centers. Transverse common tangent is a tangent touching two circles at different points and intersecting the line of centers between the centers. And common tangent at a point of contact is a tangent touching two circles at the same point. Such a tangent exists only when the circles touch each other externally or internally. So our idea is clear now. So now what we are going to do, we are going to explore more on this, okay? And we'll see that how how we can form different kind of tangents and their relevant discussion. So to do this thing, let us consider two circles. That one circle is S1 equal to 0, another circle is S2 equal to 0, and we are assuming their centers at the point C1 and C2, and their radii is R1 and R2. So what we are going to discuss now, the condition for the above three types of tangents. So what we are going to discuss now is the condition of the above types of tangents, whatever we just introduced to. That is direct common tangent, transverse common tangent, and common tangent. And for that, what we are assuming that the equation of the circles is S1 equal to 0, S2 equal to 0. Two circles, so two equations. The first one is S1 equal to 0, and second one is S2 equal to 0. So S1 equal to 0, first circle, S2 equal to 0, second circle. And the first circle is having the center at C1, second circle is having center at C2, and R1 and R2 are their respective radii. Correct, dear students? Clear? Now first we are going to discuss is that, that the case 1, when the distance between the centers is greater than R1 plus R2, and R1 is not equal to R2. So what is the case, dear students, here? The first case what we are going to discuss here, that when the distance between the centers, that C1, C2, the distance between the centers is greater than R1 plus R2, the sum of their radii, and these two circles has different radius. That means R1 is not equal to R2. So if we give a pictorial description of this case, then how it looks like? So it looks like something like this. Okay, dear students, at any point of time, any difficulty, never hesitate to let me know. So what we see is that if you see the 2 points, that C1, this is the point C1 and C2. The distance between C1 and C2 is more than the sum of their radii R1 plus R2. So in this case, what we see is that direct common tangents are this one. This is direct common tangent. This is direct common tangent. And what is the transverse common tangent? Already marked it actually. This is transverse common tangent. This is transverse common tangent. And C1, C2 is a line is also mentioned. So this is transverse common tangent. Correct? Now, As we see from the diagram, uh, we have four common tangents, two direct and two transverse. Now let the direct common tangents meet at the line of center at the point P, as you see in the diagram. So that means the direct common tangents meet at the point P, and the transverse common tangents meet at the point Q. So these are the transverse common tangents, they meet at the point Q. You know, dear students, there is an interesting relationship. The point P divides the line segment C1, C2 in the ratio R1 is to R2 externally, and the point Q divides the line segment C1, C2 in the ratio R1 is to R2 internally. Let me repeat once more, dear students, is that the point P, okay, so if I write down this thing, and then let me explain. So these two are very important piece of information, is that so what I'm saying is that, you know, the point P, which is the point of intersection of the direct common tangents, okay, then the point P divides C1 C2 in the ratio R1 is to R2 externally. What does it mean? It means is that C1P is to C2P is equal to R1 is to R2. C1P is to C2P is equal to R1 is to R2. Correct? And Q divides, so if I use a different color, and Q divides C1, C2 in the ratio R1 is to R2 internally. That is what, dear students, from this statement, what we can say, that C1Q is to C2Q is equal to R1 is to R2. Clear, dear students? So these are the information we are able to make it. Now, if you want to have a proof about it, so that we can take a separate session to prove it. But most importantly, we need to know about this information. Now, the next point what comes here is that under this case is that how to find the direct common tangents. To find the direct common tangents, find equation of the tangents to any of the two circles through the point P, that you can find it out. That equation of the tangents from an external point P to any of the circles that we have discussed. And for transverse common tangent, find equations of the tangent through Q to any of the given circles. Correct? So that is the way, and how to do this thing that we have discussed in one of our previous sessions, that how to find the equation of these tangents. That means from the point P, what I'm mentioning, so let me put it from the study material and then explain. To find the direct common tangent, the equation of the direct common tangent, what you need to do. So from this point P, we know, from an external point P, what are the equation of the tangents to any of the two circles. And for the transverse common, for the equation of the transverse common tangent, we can find the equation of the tangent to any of these circles from the point Q. Correct? In that way, we can find the equation of the transverse common tangent. So this is about the case 1, dear students. Now, we are going to discuss about the case 2, where C1, C2 is greater than R1 plus R2, like the case 1, but here R1 is equal to R2. So let's see what kind of configuration we are going to get. First, we need to give a visual representation of this case. So what is the case we are going to get it here, dear students? Is that C1, C2 is equal to R1 plus R2, and in this case R1 is equal to R2. So what will be the visual representation of this particular case? So I'm going to show you that one. I hope you are able to view it, dear students. So if you look into this particular diagram, you'll able to make sense that why what is happening when it is R1 R1 is equal to R2. In this case also we have four tangents, two direct common tangents and parallel to the line of the centers, as you see in this diagram. So these are the direct common tangents. So this one, this line and this line, they are parallel to the line of centers, and two transverse common tangent, okay, meeting at the line of the center C1 C2 at Q. You see, so what we get, the direct common tangents. So this is this one and this one is a direct common these are the direct common tangents. And what are the transverse common tangent? So we get this one. So this is transverse common tangents. Okay, got it? So now for direct common tangent, okay, find the tangent to any of the circle having slope m, okay, of the line C1 C2, and that how you can find it out? Y minus y1 is equal to m into x minus x1 plus minus r1 into square root of 1 plus m square. Correct or not? So what I'm going to what I'm meaning it here. So where the point x1 y1 is C1, R1 is the radius, and circle S1 equal to 0, and m is the slope of the line C1 C2. So what I wanted to mean is that if we take that the for the direct common tangent, so how we can find the equation? Okay, so for the direct common tangents, dear students, let me show you here. For direct common tangents, it is actually plural number, there are two. For the direct common tangents, find the tangent to any of the circle having slope m of the line C1 C2, because direct common tangents are parallel to C1 C2, so they will have the same slope like C1 C2 line. For this, how we can use? We can use this equation, dear students. If you recall this equation, we have discussed about these equations earlier. Okay, y minus y1 is equal to m into x minus x1 plus minus r1 into square root of 1 plus m square. So here x1 y1 is what? Is the coordinate of the center C1. So what I say is that x1 y1 is the coordinate of the point C1. R1 is the radius of the circle S1 equal to 0, that is the first circle, or we can say that R1 is the radius of the circle with C1 as center, and m is the slope of the line C1 C2, that is the line of centers. And if you notice, dear students, there is a plus minus sign. Plus 1, that means there are two straight lines. One straight line representing the first direct common tangent, the other one represents the second the other common tangent. So if you take plus for this one, okay, that minus would be for this one. I hope it is you got this point about the direct common tangent in this particular case. Now, dear students, what we can say is that for transverse common tangent, how we can do it? Find Q, which divides the C1 C2 in the ratio R1 is to R2 internally. Then find tangent from Q to any of the circle, as we discussed in the previous case. So So whatever I marked in that red box, that equation, that is for the equations of the direct common tangent. And for the transverse common tangent, okay, what we can do is that first we can find the coordinate of the point Q. It is very easy to find the coordinate of the point Q. How? Because we know that point Q divides the line segment C1, C2 in the ratio R1 is to R2. We know R1, we know R2, we know coordinates of the point C1 and C2. So it is very easy to find the coordinates of the point Q. Now, once we find that Q, now which then find the tangents from Q to any of the circle as we have discussed in the previous case. Okay. So in that way, we can find the equation of the transverse common tangent. Okay. Now, here one important result I would like to mention, dear students, is that the common tangents, direct or transverse, okay, is bisected by their radial axis. I repeat, the common tangents, direct or transverse, that means segment of the common tangents between their respective points of contact, is bisected by their radial axis. If you want, you can prove this thing also, okay, and these are a very important thing. But my primary task is to inform you about this statement, because these statements are important to while solving problems. Okay. And while solving problems, this information has to be very handy to you. Means it is you can just recall this information and start solving the problem based on these concepts. Okay, but to prove this kind of step, that you can do it your own, or you can take my assistance later. Now we are going to discuss about the third case, okay, where C1, C2, the distance between the centers is equal to R1 plus R2, and R1 is not equal to R2. So let's see what is going to happen in this particular case. Okay, so case 3, what we are going to discuss, dear students, is that R1 C1, C2 is equal to R1 plus R2, in which case that R1 is not equal to R2. So let me give you a visual representation of this case, dear students, so that it will make more proper sense to you. So what does it mean by this? The moment you see that C1, C2 is equal to R1 plus R2, one thing to pretty sure that these two circles are these two circles touch each other externally. Okay, what does it mean? So and the moment it comes to our mind that these two circles touch each other externally, that means this kind of diagram comes to our mind, and here is the visual representation. If you notice, dear students, in this case the circle S1 equal to 0 and S2 equal to 0 touch each other externally. Now we have in all there are if you see, there are 3 common tangents. One common tangent touching both the circle at the same point Q, and 2 direct common tangents meet at the point P. So that means if you see that these are the 2 common direct common tangents. So this is a direct common tangent, this is the direct common tangent. So let me write it down. These are direct common tangents. And if you look into the other straight line, which is passing through the point Q, okay, and touching both the circles, okay, so this is a common tangent, right? So this we can say is a common tangent, correct, dear students? Okay. Now the point Q, we know that it divides C1, C2 in the ratio R1 is to R2 internally, and the point P divides the line segment C1, C2 in the ratio R1 is to R2 externally. That we know from the case 1. So equations of the direct common tangents can be found as in the previous cases what we discussed, and the common tangent by the line S1 minus S2 equal to 0. Thus, we have a triangle ABP formed by the common tangents. Correct not? You see that AB is a common tangent, and AP and BP are the two, direct common tangents. So these three actually form a triangle ABP. Now, before I'm going to discuss about this triangle, I just want to reiterate whatever I said a minute back. How to find the equations of the direct common tangents? That is like the previous cases. Okay, because we have the information that the point P divides the line segment C1, C2 in the ratio R1 is to R2 externally, and the point Q divides the line segment C1, C2 in the ratio R1 is to R2 internally. So, equations of the direct common tangents can be obtained as in the previous cases. That is, from a external point you are drawing two tangents. What is the equation? You can find it out. But the point is that here the new thing is that what is the equation of the common tangent, that is AB? Okay, its equation, what will be known, dear students? Its equation will be S1, let me write properly. Sometime in the digital board I cannot write properly. S1 minus S2 equal to 0. Where S1 equal to 0 is the equation of the first circle, that is S1 equal to 0. And S2 equal to 0 is the equation of the second circle. Then the equation of the common tangent should be S1 minus S2 equal to 0. Now let me come to the triangle what I was talking about. So now what we see is that we have a triangle ABP formed by these three common tangents. Two direct common tangents AP and BP, and the one common tangent, that is AB. So now we have points P and Q. We know we can find the coordinates of the point P and Q. So clearly the common tangent AB bisects T1, T2. That is quite sure. So then what we can find it out about the AP is equal to BP is equal to nothing but 1 by 2 of PT1 plus PT2. That is the length of the tangents. Okay, so let me give you this particular a mathematical expression, and then we can discuss the relevant points. So what I wanted to mean here is that, dear students, is something like this. Could you please confirm that you are able to view the screen? This particular text is fine, or shall I need to put it in the below of this diagram? Is it fine? Can someone please confirm? Okay, it's fine, right? Okay, it's fine, dear student.
Yes.
Okay, so what we see is that if you look into that area of the triangle ABP, we have the.
Sir, can you increase the font?
Okay, all right. Let me increase the font then. Okay, just a minute. Let me put it here. Okay. I hope it is fine now. Is it fine?
Sir.
Okay. So now, if you look into this, we have we are going to find the area of the triangle ABP. How we are going to find the area of the triangle ABP? We have the points P and Q. We know we can easily find the coordinates of the point P and Q because of that internal P is that externally divide the line segment C1, C2, and Q internally divide the line segment C1, C2. Now clearly the common tangents AB, okay, bisects that T1, T2. Okay, so now as this is the case, then what we can do is that we can find AP. Okay, AP is equal to BP, and that is equal to half of PT1 plus PT2, correct? And PT1, we can find it out is that PT1 is equal to what is the length of the tangent. That is, in that equation of the circle, you just replace the value of P. The coordinate of P means X coordinate of point P should be replaced by x in the equation s1 equal to 0, means we'll take that expression s1. Similarly, s2p, so that we are able to find it out, ap equal to bp. Correct, dear students? And the next point what we are going to do is that that AB is equal to AB, that is S1 minus S2 equal to 0, that is the equation of the common tangent, is perpendicular to the line of the centers. That means that angle AQP is equal to 90 degree. So from the Pythagoras theorem, what we can find that AQ is equal to square root of AP square minus PQ square. Okay, that we can find it out. AP we found it out, and we found it out is that PQ as well, because we know the coordinates of the point P and Q. So we found the value of AQ. So now as we know that AQ, then it is very easy to find the area of the triangle ABP. How we can find the area of the triangle ABP, dear students, is equal to half into base into altitude. So half into here the altitude is PQ and base is actually AB, okay, which is half of AQ, correct? So AQ is 2 times of AQ is that is the base, that is AB. So in that way, what we can find is that AQ into PQ, that is the area of the triangle ABP. I hope you got it very clearly that how to find that equation, find the area of the triangle ABP. Now we are going to discuss the next case, that is case 4, that is when C1 C2 is equal to R1 plus R2 and R1 is equal to R2. So let's visualize this case again, because visualization makes a lot of sense here. So what we are going to do, dear students, is that so what we get it here is that C1 C2 is equal to R1 plus R2 and R1 is equal to R2. So what is this case? Let's understand. Okay, so the visual representation looks like this. Now in this particular case, the two common tangents parallel to the line of the centers, that is quite evident, and that one common tangent, that equation is S1 minus S2 equal to 0. So we can easily find the equation of these three common tangents. That is pretty simple. Now let's come the next case, that is case 5. What is that? In this case, that the mod of R1 minus R2 less than C1 C2 less than R1 plus R2, in which case R1 is not equal to R2. Okay, so let me show you this particular case, then it will be very clear to you. So what is the case we are going to discuss here, dear students? It is something like this. That this is case 5, that where mod of R1 minus R2, that is the non-negative difference between the the radius, okay, is less than C1 C2 is less than R1 plus R2. So what will be the visual representation of this particular case? So it will be something like this. Let me show you. So its visual representation will be something like this. Correct, dear students? This is properly give a visual representation of that inequality, that mod of R1 minus R2 is less than C1 C2 less than R1 plus R2. Now in this case we have only two direct common tangents. You see, there is no other tangent, either common tangent or transverse common tangent. Only we have two direct common tangents whose equations can be found as we discussed in the previous case, because we know the coordinate of the point P. From the outside of the point P, we know how to find the equation of the two tangents. So it is quite simple in this case also. Okay. Now let's come to the next case, that is case 6. In the case 6, what we are going to do, dear students, is that when we have that 0 less than C1 C2 less than R1 plus R2. So let me like the previous case, let me give you a visual representation of this case. So the case here, dear students, is that 0 less than C1, C2 less than R1 plus R2. So what will be the visual representation of this statement of this inequality? So it will be something like this. Correct, dear students? Okay. Now, if you look into this particular scenario, in this case we have only two direct common tangents, like exactly the previous one, and that is parallel to the line of their center. So finding equation is not difficult; it is very straightforward. The next case, that is case 7, is that where C1, C2 is actually equal to the non-negative difference of R1 minus R2, in which case R1 is not equal to R2. Okay, let me show you this particular case with the visual representation, and then let's discuss after that. So if we give a visual representation of this particular case, the case 7, it is something like this. And I hope you are able to, resemble, you're able to make sense that, about the, whatever I draw, wrote the linear, equation, that C1, C2 is equal to mod of R1 minus R2, where R1 is not equal to R2. That means these two circles touches each other internally. Now, as we see these two circles touches, each other internally, therefore we have only one common tangent, and that equation is S1 minus S2 equal to 0. It is pretty simple. What will be its equation? Its equation will be S1 minus S2 equal to 0. Now let's proceed to the next case, dear students. That is case 8. What is that? In this case, that C1, C2 is either equal to 0 or C1, C2 is less than mod of R1 minus R2. So what does it mean by C1, C2 is equal to 0? C1, C2 is equal to 0 means what? They has to be, concentric circles, correct or not? So if I give you there is a little mistake has happened here, a small mistake. So let me correct it. So the mod I actually mistake here, and it is only case 8. So case 8. Okay, what is this case here, dear students? That C1, C2 is either equal to 0 or C1, C2 is less than R1 minus R2. So what does it mean? It means is that these two, one circle is completely contained in the other. So what will be the visual representation of this case? The visual representation of this case will be something like this. Okay. Now, if you look into it, it is quite evident in this case, no common tangents is possible. Okay, dear students. So, these are the points what I wanted to discuss about the common tangents, and I hope things are clear. And I would like to conclude the class here, dear students, and we will have our next class tomorrow, same time, in which we'll make some practice from circles. With this note, let me complete the class now. Thank you very much.